The nature of matter. What three subatomic particles make up atoms? The subatomic particles that make up atoms are protons, neutrons, and electrons. Protons and neutrons in here, electrons have what we call orbits in location. The study of chemistry begins with the basic units of matter, the atom. The concept of the atom came first from the Greek philosopher Democritus, nearly 2,500 years ago. Democritus asked, "Can you divide a substance without limit, or does there come a point at which you cannot divide the substance without changing it into something else?" Democritus thought that there had to be a limit, and he called the smallest fragment atom the Greek word atomos, which means unable to cut. Atoms are incredibly small. Placed side by side, 100 million atoms would make a row about 1 centimeter long, about the width of your little finger. Despite its extreme small size, an atom contains subatomic particles that are even smaller. The subatomic particles that make up atoms are protons, neutrons, and electrons. 3 subatomic particles in a carbon atom are shown in the diagram. Protons with the positive sign, neutrons, and electrons. Protons and neutrons have about the same mass. Protons are positively charged particles, and neutrons carry no charge at all. Strong forces bind protons and neutrons together to form the nucleus of the center of the atom. They're called strong because look how close the equal charges are together. It has to be something that holds these close together because they normally repel. The electron is a negatively charged particle with only 1 out of 2,000 or so, 1 out of 1,840 portion of the mass of a proton. The electrons are in constant motion in the space surrounding the nucleus. They are attracted to the positively charged nucleus, but remain outside the nucleus because of the energy of their motion. Because atoms have equal numbers of electrons and protons, their positive and negative charges balance out, and atoms themselves are electrically neutral. The carbon atom shown has 6 protons and 6 electrons. How are all the isotopes of an element similar? Because they have the same number of electrons, all isotopes of an element have the same chemical properties. A chemical element is a pure substance that consists entirely of one type of atom. More than 100 elements are known, but only about 24 are commonly found in living organisms. Elements are represented by 1 or 2 letter symbols. For example, C stands for carbon, H stands for hydrogen, N small a for sodium, and H small g for mercury. That's a picture of mercury. It is a liquid at room temperature. The number of protons in the nucleus of an element is called the atomic number. Carbon's atomic number is 6, meaning that each atom of carbon has 6 protons and consequently 6 electrons. Atoms of an element may have different numbers of neutrons. For example, although all atoms of carbon have 6 protons, some have 6 neutrons, some 7, and a few have 8. Atoms of the same element that differ in the number of neutrons they contain are known as isotopes. Carbon 12, number of protons, number of protons has to be 6, and number of electrons also 6. But the number of neutrons that are neutral in charge could be 6, which is the most stable state. And then also could be 7, still somewhat stable. And then 8. If it's 8, it's radioactive and it will decay. It will fall apart. The total number of protons and neutrons in the nucleus of the atom is called the mass number. Isotopes are identified by their mass numbers. For example, carbon 12, carbon 13, and carbon 14. So it's 6 plus 6 is 12, and 6 plus 7 is 13. 6 plus 8 is 14. The weighted average of the masses of an element's isotopes, in which the abundance of each isotope in nature is considered, is called its atomic mass. Because they have the same number of electrons, all isotopes of an element have the same chemical properties. Some isotopes are radioactive, meaning their nuclei are unstable and break down over time at a constant average rate. Although radiation can be dangerous, radioactive isotopes have a number of important scientific and practical uses. Geologists can estimate the age of rocks and fossils by analyzing the isotopes found in them currently, after making an assumption of the initial amount of isotope present. Radiation from certain isotopes can be used to detect and treat cancer and to kill bacteria that cause food to spoil. Radioactive isotopes can also be used as labels or tracers to follow the movement of substances within organisms. In what ways do compounds differ from their component elements? The physical and chemical properties of a compound are usually very different from those of the element in which they are formed. Some are more stable and some are more volatile or reactive. A chemical compound is a substance formed by the chemical combination of two or more elements in defined proportions. Scientists show the composition of compounds by shorthand known as chemical formula. Water, which contains two atoms of hydrogen for each atom of oxygen, has the chemical formula H2O. The formula for table salt, NaCl, indicates that the elements that make up table salt, sodium and chloride, combine in a 1-to-1 ratio. The physical and chemical properties of a compound are usually very different from those of the elements from which they formed. For example, sodium is silver-colored metal that is soft enough to cut with a knife. It reacts explosively with cold water. And chlorine is a very reactive, poisonous greenish gas that was used in battle during World War I. However, together is table salt as a white solid that dissolves easily in water and is not poisonous and is essential for survival of most living things. What are the main types of chemical bonds? The main types of chemical bonds are ionic bonds and covalent bonds. Ionic bonds, where one donates an electron to the other, and by that one becomes positive, and this one becomes negative, an extra negative charge, and they are bound together because of the donation. And here, their covalent bond, they're sharing one of these electrons each. So hydrogen is sharing an electron with oxygen, and this would complete the orbit over here and get rid of one to reduce the orbit over here. Had one extra and it binds with the chlorine. So they're making a solid 8 on the outside here, and 8 is the last on this one, donating that extra one. And here is 8, but only 8 with these shared electrons from the hydrogen. And the initial orbit is only 2. Hydrogen has 2, and that's complete orbit, and 2 complete orbit here. The atoms in compounds are held together by various types of chemical bonds. Bond formation involves electrons that surround each atomic nucleus. The electrons that are available to form bonds are called valence electrons. In ionic bonds, an electron is handed over. In covalent bonds, the electrons are shared equally. An ionic bond is formed when one or more of the electrons is transferred from one atom to the other. An atom that loses electrons becomes positively charged. An atom that gains electrons has a negative charge. These positively and negatively charged atoms are known as ions. Ionic bonds form between sodium and chloride to form NaCl, table salt, sodium chloride. So it transfers an electron, and that makes this 8 on the outside and 8 on the outside. It makes it balanced on the electron orbits, but it's missing one. It has a positive charge, and now it has an extra electron, and Because it has a negative charge and a positive charge, they attract each other. Opposites attract. A sodium atom easily loses its one valence electron and becomes a sodium ion, Na plus. As it loses an electron, it has an extra imbalance of +1. A chlorine atom easily gains an electron from sodium and becomes a chlorine ion, Cl negative. And that is because it has an extra electron. These oppositely charged ions have a strong attraction to each other, forming an ionic bond between here plus minus. So in covalent bonds, sometimes electrons are shared by atoms instead of being transferred. The moving electrons travel around the nuclei of both atoms, forming a covalent bond. So between hydrogen, to complete an orbit, needs two, so they're traveling around both. When the atoms share two electrons, the bond is called a single covalent bond. Sometimes the atoms share four electrons and form a double bond. In a few cases, atoms share six electrons, forming a triple bond. So here is a single covalent bond. Chlorines was missing one, so the two chlorine atoms share one, so complete the orbits of 8 for both. Here, hydrogen chloride, a hydrogen has just one, needs one more to complete the first orbit of 2, and this needs an extra one for 8. And ammonia, same idea, nitrogen was missing 3. So shared one with hydrogen in 3 places. The structure that results when the atoms are joined together by covalent bonds is called a molecule, the smallest unit of most compounds. This diagram of water molecule shows that each hydrogen atom is joined to water's lone oxygen atom by a single covalent bond. Each hydrogen atom shares 2 electrons with the oxygen atom. The electrons that are available to form bonds are called valence electrons, found in the outermost orbit. When atoms of the same element join together, they also can form a molecule. Oxygen molecules in the air you breathe consist of 2 oxygen atoms joined by covalent bonds, sharing 2 each to complete 8 electrons in that orbit. So there are 6 electrons in this oxygen atom and 6 electrons in this oxygen atom in the furthest orbit. So they share 2 each, a double bond. And the last force, van der Waals forces. Because of their structure, atoms of different elements do not have the same ability to attract electrons. Some atoms have a stronger attraction for electrons than do other atoms. When the atoms in a covalent bond share electrons, the sharing is not always equal. Even when the sharing is equal, the rapid movement of electrons can create regions of molecules that have tiny positive or negative charge. When the molecules are close together, a strong attraction can develop between the oppositely charged regions of nearby molecules. These intermolecular forces of attraction are called van der Waals forces, after the scientists who discovered them. Although van der Waals forces are not as strong as ionic bonds and covalent bonds, they can hold molecules together, especially when the molecules are large, and the gecko will show us how. These are gecko foot hairs. With increased surface area, they are able to carry weight of the gecko because the van der Waals forces between the gecko hair ends and other surfaces will hold the gecko on the wall or even on the ceiling.